Good evening, all. Fine. See, let us start the session. See, what we have seen in our last class, we are discussing about flip-flops, right? So we are discussing flip-flop circuits, right? So yesterday we saw how to design the flip-flops. So we saw there are 4 types of flip-flops, right? First, what we saw, SR flip-flop, and then we saw the design of JK flip-flop, and then we saw the design of T flip-flop and D flip-flop, right? So please refresh your notes once again. Please open and see the characteristic table and excitation table, right? Just keep it with you, because now we are going to see the second part of the flip-flops. See, when I was discussing about the designing of the flip-flop, I only told you, right, we can bring any flip-flop from any flip-flop. That could be possible, right? I only told you that one, right? Now, that is what we are going to do. Let us take the various types of flip-flop. Let us see how to design, right? So, how to design T flip-flop, D flip-flop from, that is D, T, JK from SR. And again we will see, we will take JK flip-flop and we will design some other type of flip-flops, right? So we are not going to design all those things, right? I will design some flip-flop such that you will get the clear idea. Then you will be able to design all type of flip-flops, right? Fine. So let us start this session with the first one. Now, I would like to design. See, we know the truth table of SR flip-flop, right? And we also know the characteristic table, excitation table. Just keep them all with you. I need 2 tables here, right? One is characteristic table and another one is excitation table of the flip-flops, right? So, they are the main people that we are going to use them in order to design the flip-flop circuits, right? Okay. Let us see. The first thing is, I told you, right, with the help of SR flip-flop, we can design JK flip-flop. Do you all agree with me? Yes. So, let us see. The first circuit that I am going to consider now is, let us design the JK flip-flop with the help of SR flip-flop, right? So the first target is, let us take JK flip-flop, right? The thing is, we are going to use SR flip-flop, right? We are going to use SR flip-flop in order to design JK flip-flop, right? So I would like to implement JK flip-flop with the help of SR flip-flop, right? So let us see the implementation procedure, right? Guys, listen. So that is called a conversion, flip-flop conversion. Keep that in. We are going to discuss about flip-flop conversion. It's quite interesting actually. The thing is, you'll have to, first thing, what we are going to design, see, the thing is, we are going to design JK flip-flop, right? With the help of SR flip-flop. That is the first step. So the step number 1, you will have to write the characteristic table, right? So you will have to write the characteristic table, right, for implementing flip-flop, right? So characteristic table for implementing flip-flop. Which flip-flop that we are going to implement now? We are going to implement, right? So that is implementing flip-flop, in the sense we are going to implement what? JK flip-flop. So step number 1, write the characteristic table for implementing flip-flop, right? So here I am implementing what? We are implementing what I can say, JK flip-flop, right? And second step, write the excitation table, right? So immediately we will have to write excitation table for using flip-flop, right? So which flip-flop we are going to use, right? We are going to use what? SR flip-flop, right? So we are going to use SR flip-flop, right? We will have to write the excitation table for SR flip-flop. So step number 1, we have to write the characteristic table for implementing flip-flop. Step number 2, we have to write the excitation table for using flip-flop, right? And step number 3, we have to realize the circuit, right? So circuit realization, realize the circuit, that's all. Realize the circuit. That is, we have to design the circuit. That is the step number 3, with the help of characteristic equation, right, that we are going to obtain from the SR flip-flop, right? So realize the circuit with the, right, with the help of characteristic equation, right, with the help of characteristic equation, right? I will teach you how to get the characteristic equation. Fine. So let's start our journey with this. So first thing, we are going to design JK flip-flop with the help of SR flip-flop, right? So let's try and figure out the characteristic table of JK flip-flop, right? Now first of all, what do you mean by characteristic table? Characteristic table, in the sense, present output of the system will be predicted with the help of present input and past output. Do you all agree with me? Yes. So we all know how to write the characteristic equation. So step number 1, let me write the characteristic equation of implementing flip-flop. That is, we are going to implement implement JK flip-flop, right? So let us consider the present inputs of the JK flip-flop are J and K, and the past output of the JK flip-flop is simply called Qn, and the present output of the JK flip-flop is simply called Qn plus 1. Usually characteristic table will be implemented with the help of whom? Characteristic table usually will be implemented with the help of truth table, right? So let us see. Anyway, here we are having 8 combinations: 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 double 0, 1 0 1, 1 1 0, 1 1 1. Okay, so this is the things that we are getting, right? That is the possibilities with the input and past outputs. Now with this we have to bring the present input, right? So present output. How will you do that one? So just we have to take the truth table of the JK flip-flop. For that, in order to design the characteristic table, we have to go with the what? Truth table. Now we all know the truth table of the JK flip-flop, right? So let us write the, let me write the truth table of the JK flip-flop right somewhere here. See, K, its correspondent truth table is Qn plus 1. What we have been observed, 0 0 0 1 1 0 1 1. Let me place it here. It is Qn, it is 0, it is 1, it is going to be Qn bar. Correct? This is the truth table of our JK flip-flop. I think that portion is visible to you all. If it is not visible, just revise your notes, right? Because I have written those things already, right? We have seen it. Okay, let's proceed. See there, whenever your inputs are going to be 0 0, your flip-flop, JK flip-flop will simply follows the present, that is present in output of the JK flip-flop simply follows the past output, such that 0 1 will appear in the output side. Whenever your inputs are going to be 0 1, irrespective of the past, present output of the system will be 0. Whenever your input is going to be 1 0, irrespective of the past, present output of the system is going to be 1 1. Whenever your input is 1 1, right, your present output of the system is the complement of the past. 0 complement 1, 1 complement 0. This is how we are writing characteristic table. Now immediately after writing the characteristic table of the implementing flip-flop, our next target is we have to write the excitation table for the using flip-flop. We are going to use what? SR flip-flop, right? So that is SR flip-flop. Let us write. Let us consider, let me merge the SR flip-flop with this. The second step, we have to write the characteristic, excitation table for SR flip-flop. How will you write the excitation table? See, with the help of Qn and Qn plus 1, we will have to write the excitation table. See there, first step, we are obtaining Qn and Qn plus 1, right, for the flip-flop that we are going to implement. Just we have to make this table, and then from with the help of this Qn and Qn plus 1, we will have to write the excitation table. We all know excitation table in the sense we will have to consider the past output and present output of the system in order to guess the future, that is in order to get the present inputs of the system, right, in order to guess the inputs, possible inputs of the SR flip-flop, right. So let us write the excitation table, right. So let us consider the excitation table of the SR flip-flop that I have written it here. Okay, I hope that portion is visible. Let's see what are all the possibilities that we are going to get for 0 0. Whenever that is 0 0, we are giving 0 0, the possible output is going to be 0x. If we are giving 1 1, its possible output is x0. If you are giving 0 0, again it will become 0x. If you are giving 1 0, that is this is for 0 0, this is for 0 1, this is for 1 0. For 1 0 we are getting 0 1. If you are giving 0 1, then we are getting 1 0. If you are giving 1 1, then we are getting x 0, right. If you are giving 0 1, right, so if you are giving 0 1, then we are getting 1 0. If you are giving 0 1, then we are getting 1 0. If you are giving 1 0, then we are getting 0 1. This is the excitation table, right. So that is how we are writing the excitation table for the flip-flop that we are going to use. Now after designing this one, immediately next we will have to find out the characteristic equation first in order to implement this circuit, right. Usually we are finding the characteristic equation with the help of what K-map, right, when we have 8 possible combinations, right. So let us see, first take S flip-flop, S line, right. Let me implement them into the K-map in order to visualize the output, right. Let us see, let us substitute the variables here. So totally we have to consider 8 adjacent cells, that is 8 cells, right, and its possible inputs. Guys, listen. Now here, in order to identify the characteristic equation, right, so for this S, we will have to consider the present input and past output of the system. Let us see, here actually we are going to consider J bar J, that is I would like to write it in SOP form, right. So here it is going to be K bar Qn bar, and we are considering K bar Qn, Here we are going to consider KQN. Here we are going to consider KQN bar. Let us place the values, right? So for S, see, actually I am writing this table for S, for this person. Let us consider for S, 0 I don't have any variable. At 1 we have the variable, 2 we don't have any variable, 3 we don't have any variable, 4 we have, 5 we have, 6 we have, 7 we don't have any variable. Now let us write the output for this function, right? So the output of this S is going to be, simply let us see there, directly we can club these two person, right? Unnecessarily we know to use the don't care here, it is not required for us, right? So let us write the output is going to be J, this is J, and the common term between these two guys is going to be what? QN bar. Clear? So for S flip-flop we have to consider J as the input, and we have to consider KN bar also with this, right? So let us consider this is the output of S, that is the input of S, right? So let us write the same thing for second output, that is R. R ku neenga idhe eludringa appadina, let us see, right? So let me place them into the K map once again. Let us place them, right? So we have to consider 8 cells, 8 possible combinations, right? And first of all, directly we will register the variables. What we have for 0 we have variable yes, for 1 no, for 2 we have yes, for 3 we have, for 4 we don't have, 5 we don't have, 6 we don't have, but 7 we have. So such that we can group these two person directly. See, actually what I have there, this is the input of R. R என்ன வரும் பாருங்க, இந்த இடத்துல யார் இருக்கா? Exactly here, K into Qn. இந்த பிளேஸ்ல யார் இருக்கா? K into Qn. Directly we are going to get that one as the input for R flip-flop. So after obtaining the characteristic equation, we will have to realize this circuit. We will have to realize this circuit. Let us realize this circuit. The thing is, we are implementing JK flip-flop with the help of SR flip-flop, right? So let us consider the general representation of the SR flip-flop is like this. This is S. Here we are going to consider R, and I said this is simply we can treat this one as Qn and this one as Qn bar. That is the general representation. See, whenever we are writing Qn plus 1 with the Qn, in that case Qn is being treated as past and Qn plus 1 will represent the present. In general we are using what? Qn and Qn bar only in order to represent the bits in the output side. Fine. Now let us design the circuit. This is general representation of SR flip-flop, right? Now what we have to do? We have to use the SR flip-flop in order to design the JK flip-flop. See there, input of the S is going to be what? J dot Qn bar, right? So let us give J Qn bar. Let us give that one. Carefully observe this one. This is what? Under operation, J dot Qn bar. Where is Qn bar? This is Qn bar, right? So let me bring a line from here. Such that, see there, and here we are going to give J as the input. Qn bar is coming from here, so Qn bar into J is going to be the input of S, right? Am I correct? This is the same thing that we have done in our last class. That's what I had been told you. This is called flip-flop conversion. So this is the equivalent circuit of the JK flip-flop, right? So let's continue. R is going to be K dot Qn, right? So K we have to give as the input, right? So let us consider. Here I am going to give K, whereas Qn is where? We will have to take one more line from here. This is going to be Qn. So this is the equivalent circuit. That is how we are realizing any circuit with the help of, guys listen, just should try to understand the procedure, because the problem is, I already told you, from flip-flop in your examinations at all, usually you will be tested with some general circuit, right? They will design some new circuit and that will be given to you in your examination. They will give you the what I can say, some data they will give you, like in order to bring the truth table and the excitation table, they will give you some set of ideas. With that you will have to bring these things and then you will have to realize the circuit, right? So don't memorize anything, just to simply understand, that's enough. Okay, fine. So this is how we are designing JK flip-flop with the help of SR flip-flop, right? So let us design few more things, right? That is few more circuits for your best understanding. So let me rub this one, right? Okay, we will keep these statements for understanding, right? So let us remove these things. Okay, next second, I think for D flip-flop also I took SR flip-flop only, right? So let us see that one, right? So the next circuit that we are going to design now is what we are going to design, let me consider SR flip-flop once again, and we are going to design D flip-flop from SR flip-flop. D flip-flop from SR flip-flop, right? So let us see how to design that one. So once again, what we have to realize realize here, step number 1, we have to consider the characteristic table of the flip-flop that we are going to implement. Which flip-flop we are going to implement now? D flip-flop, right? So let us write the characteristic table of the D flip-flop. In order to write the characteristic table, we need two persons. One is present input of the system, another one is past output of the system. That is the two cases. That is very important, right? Now here we may have four possible combinations: 0 0, 0 1, 1 0, 1 1. For D flip-flop, we have only one input, right? Now let us see the possible outputs. That is the characteristic table. In order to write the characteristic table, anyway, we are going to travel along with the what? Truth table of the D flip-flop, right? We know the beauty of the D flip-flop is irrespective of the past. If your input is 0, output also 0. Your input is 1, output also 1. That is the beauty of the D flip-flop. If I'll give 0, here also we are going to get 0. If I'll give 1, here we are going to get 1. That is the characteristic table of the D flip-flop. Let us implement the excitation table. See the excitation table of the flip-flop that we are going to use, right? We are going to use what? SR flip-flop, right? So let us write the excitation table for the SR flip-flop. Let us write down the excitation table for SR flip-flop, right? So let us consider S and R here. How will you write the excitation table, right? So let us consider, see actually what we are doing here, we are trying to write the excitation table for SR flip-flop, right? Now where we have, this is the excitation table for SR flip-flop, right? So in order to write down the excitation table of any flip-flop, we need two persons. One is past output, another one is present output. We know the past output and the present output combination here. Now if you are passing 0 0, what will happen? Immediately output is going to be 0x. Sorry, the possible inputs, when we are getting 0 0 as the possible outputs, when we are going from 1 to 0, right? See, this is for 0 0, this is for 0 1, this is for 1 0. 1 0 means its possible inputs are 0 1. For 0 1, its possible outputs are 1 0. For 1 1, its possible outputs are x 0. That is, possible inputs are x 0. So this is the excitation table of the SR flip-flop for the given circuit. I hope things are clear to you all. Immediately after completing this one, we will have to realize these things with the help of K-map, or you can directly write this statement. Anyway, you can also put it into K-map in order to realize the output, right? Okay, I don't want to waste my time. Let me write the equation directly. For S flip-flop, what we are going to get, let us write. For 1, actually we have to consider present input and past output, right? Yes, in order to write down the equation. See, here we are getting two terms, right? So see, the thing is, we don't know whether this don't care is necessary or not, right? So let me put it in the K-map, right, in order to realize whether the don't care is useful as for us, that is useful for us or not, right? Yeah, let me write this one. So let us place the values, right? So we are going to consider two variables here, right? That is, sorry, two inputs, D and Qn. So such that we are considering D bar here and we are going to consider D here. Qn bar here, we are going to consider Qn here. Let me place the variables, right? So 0 0 1, we don't have any variables. 2 we have, 3 we have. Yes, the thing is, we can group them together such that what will happen, this is the equation for S. So S is equal to, here we are considering only what? D. Directly we can write S equal to D, first data. I am grouping this one such that here you are getting 1, here you are getting D, 1 into D will become D only, right? So let me write the second one in order to obtain the equation for R, right? So once again, for R also we are getting what? Here we are getting X, here we are getting 1. If I'll club this one, correspondent, what we have here? D bar. So what is the conclusion? For R, I'm in need of D bar. So what we have understood here, which flip-flop that we are going to implement? We are going to implement D flip-flop. Which flip-flop that we are going to use? We are going to use SR flip-flop, right? So let me write SR flip-flop circuit first, right? Let us realize the SR flip-flop, because we are using SR flip-flop in order to implement the D flip-flop. So SR, here it is going to be Qn, and this one is going to be Qn bar. But the thing is what? S is equal to D. It means directly we can give D as the input for S, but for R we cannot directly give. We will have to provide D bar such that, let me put, right, one inverter here and then I will group these two guys. Right, this is the same circuit that yesterday we took in order to realize the, what I can say, D flip-flop. I hope things are very clear to you all now, right? So let us design. Next, immediately we are going to design what? T flip-flop. But what we have done in order to design the T flip-flop, I hope you all remember, I took what? JK flip-flop, right? And we have seen the reasons also, right? In order to produce the toggling, right, either we can go up with the JK flip-flop or T flip-flop. Both circuits will give us the best circuit, that is best toggling mode could be achieved with the help of JK flip-flop and T flip-flop. But the option is we are always giving priority for T flip-flop whenever I'm in need of toggling, right? Toggling mode, right? The thing is, what is the advantage? In case of T flip-flop, there is only one input. With the help of only single bit, right, we can control or we can produce the toggling mode. Whereas in case of, in order to produce the same toggling with the help of JK flip-flop, I'm in need of two inputs, right? So in order to avoid those things, usually we are giving priority for T flip-flop. But the thing is what? Both T flip-flop and the JK flip-flop will produce what? That is, they can work at a very good condition of toggling mode, right? So that is a very good application that we are going to use it in future. Should try to keep those things into your mind, because in counter at all we are going to use either T flip-flop or JK flip-flop with the input as 1, because input, when your input is going to be 1 1, then only your JK flip-flop will operate at a toggling mode. Similarly in T flip-flop also, when we are giving input as 1, that is the point when your T flip-flop will going to produce the toggling mode, that is toggling output, right? So either we can use a T flip-flop or JK flip-flop in order to design what that is a counter circuit. So you'll see zone, that is the immediate after designing these things we are going to start that one only. But the thing is we have to understand, but which is the advantage here? The advantage is we can design T flip-flop instead of considering JK flip-flop, because we are having less number of inputs. Clear? That's all. See, these things at all you have to remember, right? In your examination theoretically you will be tested. In your interviews, suppose if you are going to tell like that, sir, I am very good in digital electronics, definitely you will be tested with some basic knowledge. Why we are going up with this flip-flop, and they might give some general circuit, you might be requested to design the circuit, right? Because your interviewers will always test the smartness of you, right? So you should try to understand the basics. Fine. So what we are going to do now, next target is we have to implement D flip-flop with the help of JK flip-flop, right? So let us see. Can you please try now? I know you all have understand the procedure. You will be able to design the circuits. You please try. You please try. Okay, fine. So the next type of the circuit that we are going to design now. We are going to use JK flip-flop to design T flip-flop. That's all. Shall we start? Yes. So let us take the see. First of all, what we have to do? We need to write which flip-flop we are going to implement. T flip-flop. So step number 1, we have to write the characteristic table for the flip-flop that we are going to implement. Step number 2, we have to write the excitation table for the flip-flop that we are going to use. Right? Step number 3, we can write the KMF in order to find out the characteristic equation. Step number 4, you can realize the circuit. It's over. Clear? So let's start our journey with this. So step number 1, we have to write the characteristic table for T flip-flop. In order to write down the characteristic table of any flip-flop, we need two people. One is present input, another one is past output, right? So let us see. The present input of the T flip-flop is T, whereas the past output of the T flip-flop is Qn, right? These two people may have four possible combinations: 0 0, 0 1, 1 0, 1 1. Right? Yes, they are having four possible combinations here, right? So immediately let us discuss about the next type, that is the next one, that is called Qn plus 1, because we are going to write what? Characteristic table of the system, right? So let us consider T flip-flop. We all know in case of T flip-flop, if your input is 0, then your output will become what? Qn. Whichever the value that we are having in the Qn, that will be reflected. If your input is 0, output follows Qn. If your input is 1, then output will follow Qn bar, such that 0 bar will become 1, 1 bar will become 0. Clear? So that is the characteristic table of your T flip-flop, right? Yeah. So first step, we have to write the characteristic table for the flip-flop that we are going to implement. Of course, it's over. Immediately we have to write the excitation table for the flip-flop that we are going to use. Right? So let us write down the excitation flip-flop, right? So sorry, excitation table for the flip-flop that we are going to use. Which flip-flop we are going to use? We are going to use JK flip-flop, right? So let us take the excitation table. I hope this portion is also visible to you all, right? So let me check it by myself. Yeah, that portion is visible only, right? So happily we can take that one. So let us consider. See, in order to design the excitation table, once again we need two people. One is present output and another one is past output of the system. We know both present output and past output of the system. With the help of these two, we can design the excitation table for the JK flip-flop happily, right? So let us design. When your inputs are going to be 0 0, it's correspondent. This is for 0 0, this is for 0 1, this is for 1 0, this is for 1 1. So let us design. When your inputs are going to be 0 0, automatically its excitation table will produce 0x in the output side. When your inputs are going to be 1 1, automatically your excitation table produce its possible inputs as x0, right? This is not input actually, this is output, this is input, right? At sometimes I will murmur, please forgive me, right? So immediately when we are considering 0 1 has the possible outputs, for 0 1 we are going to get what? 1x, right? So for 0 1 we are going to get 1x. See there, this is for 0 0, this is for 0 1, this is for 1 0, right? So when we are giving 1 0, we are going to get x1. Clear? So these are all the possible things, possible inputs that we are getting for J and K, right? When we are considering Qn and Qn plus 1 has the past and present output of the system, right? So with this, immediately after realizing these things, we'll have to put them into the K map in order to write down the characteristic equation, right? So let us place them into the K map, right? So let us place them into the K map, right? Yeah. Now there are 4 people. Yes, we have to consider present input and past input. So that is T bar, present input, past output, right? So T bar T, this is going to be Qn bar and this is going to be Qn, right? So this is 0. First at 1 we have the variable, right? At 2 also we have the variable, at 3 also we have the variable. Of course, see, the thing is I am in need of J. So J is what? Just we can directly group these two guys, right? 2 grouping is possible such that J will become equal to the value of T. Yeah, exactly, that is true. So let us do the same thing for the second output. The second possible outputs are, let us consider. The thing is, here we are considering T bar T and here we are considering Qn bar Qn, such that if I will place the variables, see there, for 0 we are having x, for 1 we don't have any variable, for 2 we have x, for 3 we have 1, right? Of course we can club them. Yes, if I will club these two guys together, such that what we are going to get, for K also we are going to get T only, for K also we are going to get T only. So shall we design? Yes, at last we will have to realize this circuit with the help of characteristic equation. Yes, these are all the characteristic equation. Let us realize the circuit. Actually we are going to implement T flip-flop with the help of JK flip-flop. First we need to draw the JK flip-flop. Of course, step number 1, we have to realize the JK flip-flop in order to realize the T flip-flop, right? First, yeah, we have drawn the JK flip-flop. Happily we can design the T flip-flop now, right? So various, simply T, if I will give T as the input, T and J are going to be same. Of course, T and K also going to be same. Is there any changes that we saw in our yesterday class with this one? No, they both are going to be same, right? So that is what I had been told you. Directly we can realize the T flip-flop with the help of JK flip-flop. Okay, fine. I hope things are very clear to you all. Now, in order to get the very clear idea regarding these circuits, let us take some other possible combinations. We have designed many things here, right? So now what shall we do now? Let us take T flip-flop. Let us design SR flip-flop, right? Let us design SR flip-flop with the help of T flip-flop. I am having T flip-flop with my hand. I would like to implement SR flip-flop. Let us do the inverse process, right? Yeah. Let me rub these things, right? I hope you all have understand the procedure, right? Yeah. So let us design. Yeah, now what we are going to do, we are going to design okay, let us rub this one. Let me remove this one because we are going to design implementation. SR flip-flop we are going to implement, whereas T flip-flop we are going to use, right? Anyway, what is our first task? Writing the characteristic table for the implementation, that is implementing flip-flop. Which flip-flop you are going to implement? SR flip-flop. Let us write the characteristic table. Anyway, characteristic table in the sense we need to consider S R, right? And that is present inputs under Qn, right? So we need 3 people here. One is present input of the system, right? So we are going to do that. That is present input and past output of the system, right? In order to write down the characteristic table of any systems. So the possible inputs are, let me place them. It is 0 0 0 1. Okay, let us write fully, right? So this is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. I hope this portion is visible to you all. Let me check it by myself. Yeah, that is visible to you all. So let us continue. Anyway, what we are going to do now, let us write the equation here, right? So which equation that we are going to write? The thing is yeah, wait a minute. Yeah, Fine. Now, when we are giving 0, 0 as the input for the SR flip-flop, see, in order to write these things, we need to know the, see, here, we need to know the truth table of the SR flip-flop. Just keep your focus at this point. This is the truth table of the SR flip-flop. See, if your inputs are going to be 0, 0, then SR flip-flop will simply Qn plus 1. It simply follows the value of Qn such that 0, 1. When your inputs are going to be 0, 1, output irrespective of the past, output is going to be 1. When your inputs are going to be 1, 0, irrespective of the past, output is going to be 0, 0. When your inputs are become 1, 1, right, that is called a don't care condition. We can simply call the X, X, because that is called invalid state. We all know. Fine. Now, after completing these things, immediately our next target is we have to write the equation for what I can say. Which flip-flop you are going to use? T flip-flop. You are going to use T flip-flop, right? So let us write the excitation table for the T flip-flop, right? So for the T flip-flop, I think is that visible to you all? Let me check it by myself. No, that is not visible to you all. So let me write somewhere here. See, for the T flip-flop, we have Qn plus 1, right? So we may have 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. It's possible excitation table. Actually what? For 0, 0 we are getting 0, for 0, 1 we are getting 1, for 1, 0 we are getting 1, for 1, 1 we are getting 0. That is the excitation table for the T flip-flop. So let us place them together here. For 0, 0 we are getting 0, for 1, 1 we are getting 0, for 0, 1 we are going to get 1, for 1, 1 we are going to get 0, for 0, 0 we are going to get 0, for 1, 0 we are going to get 1. See there, this is what? This is called don't care. If it is don't care, then here also we will have to place don't care only, because your outputs are what? Unpredictable. See, if it is unpredictable, then this is also what? Unpredictable. You cannot do anything with this, right? So this is going to be the excitation table of your T flip-flop. Let me repeat once again. See there, here your possible present outputs are not known. If it is not known, then how can you guess this one? That is also not known. So just to treat that one as the excitation, that is a don't care only, right? So immediately we will have to write the characteristic equation for the T flip-flop, right? So let us write the characteristic equation. The characteristic equation we will have to use K-map in order to design that one. Yeah, fine. Ellame correct eldirukoma. I am just checking by myself. 1, 2, 3. Yeah, we have to consider what? Present input, past output, such that it is going to be S bar. Yes, this is going to be R bar, Q N bar, R bar, Q N. This is R dot Q N. This is R dot Q N bar. Okay, now the thing is we have to implement the values. How will you implement the values? Let us see how to implement the variables here. So the thing is, see there, for what values we are getting the output? 0, 0, so that is 0, 0, sorry, 0, 1 also we are getting 0, and for 2 we are getting 1, for 3 we are getting 0, for 4 we are getting 0, for 5 we are getting 1, for 6 and 7 we are getting don't care. Now, of course, here there is a necessity of using don't care. If I use a don't care, then 2 grouping could be possible. I can club this two and we can club this two also. Let us write the complete equation for T. So T can be written as T is equal to, if I'll club these two, here we are going to get S, and the common variable here it is Qn, plus if I'll consider these two, here we are going to get R Qn bar. Clear? Actually what we are doing, we are trying to implement SR flip-flop with the help of T flip-flop, right? So this is a T flip-flop. Let us consider T flip-flop here. So the realization, let us realize the T flip-flop, right? So this is T flip-flop, and here we are going to consider 2 persons, that is going to be Qn bar. Let us see the output. What we need here, actually we have to use AND gate. Let me rub this portion because yeah, I hope here we need some space. Okay. Okay, let me use 2 AND gate and 1 OR gate, and then we will join this one, right? So here I am in need of, for an example, S is going to be connected with the Qn. Let me connect this one, yeah, and let us connect this one with the Qn bar, right? So let us place, this is going to be S, this is going to be R, such that, now see there, S into Qn is coming from here, so S into Qn will give you S into Qn, that is S dot Qn. Similarly, Qn bar is coming from here, such that it will going to be R dot Qn bar. Now this is OR gate now, so we are going to get S.Qn plus R.Qn bar. So that is going to be the output, right? So this is going to be the input of the T flip-flop, clear? So that is how we are realizing SR flip-flop with the help of T flip-flop. Clear? I hope things are very clear to you all, right? In the same way, you can design. So the finalized conclusion is what? We can design any flip-flop from any flip-flop. That statement is true now. That things we had been proved now, right? So guys, I am repeating once again, right? This is very simple procedure. Now you all have understand. I know that one. But the thing is, in your examination, you will be tested with some general circuit only, right? You may expect the questions from here. I cannot give guarantee for that. But the thing is, understand this procedure in order to design these circuits, any general circuits, right? Fine. So this is all about flip-flop, right? So basics of the flip-flops are over, right? Now immediately after completing the flip-flops, right? So we have to design the next part, that is second part of the circuit. That is second part of the sequencer circuit, that is called counters, right? So we are going to design counters, right? So very simply we have to understand first of all, what do you mean by counters and what we are going to do in counters, right? And we will design the there are two type of counters are there. One is called synchronized counter and another one is called asynchronous counter, right? Now what do you mean by synchronous counter and what do you mean by asynchronous counter, right? Actually there will be a difference between synchronous counter and asynchronous counter. You can simply understand. Listen, in the asynchronous counter, so basically let us start from the beginning. Okay guys, listen, we are going to design some circuits. It's simply called counters, right? First of all, what is the meaning of the counter? Counter in the sense it will going to count the variables or count the number of states, right? For example, we can design the clocks, right? So we are starting at initial counting as 0, and that is a 12 o'clock, and then 1 o'clock, and then 2. It's again counting, it's a 3, and then 4, 5, 6, 7, 8, 9, 10, 11, 12. Again we are getting back. So we are going to design, that is we are going to count the states, right? So we are going to count the states. Like we can count counter abdina counting na just we are counter abdina counting the variables. Like now we can consider 0 at the state on the 1, next to 2, 3, 4, 5, 6, 7. Like that we can count, or we can count the values in the reverse order. Like you can start from 10, you can come back to 9, and then 8, 7, 6, 5, 7. Or you can count the values like this, 1 and then 3 and then 5. That is odd counting, 7, 9, 11. Or you can count like this, 2, 4, 6, 8, 9. Or you can count some random variables like start from 1, 3, 7, 2, 4, 34. Immediately you may come back 24. Again you are getting that is getting back to 0, and then we are getting 0, 3, 2, 1, again 0, 5, 9, 11, again 9, again we are getting 8, 5, 3, 4. What is this? This is random sequence. So counter in the sense it is the general meaning. And now the specific idha nama count panna appadina solla. So what we are going to do, we need counter in the sense commonly endha mari or order neenga koduthalum adha vandu nama count panni kodukanum. That is simply called counter, right? So what we are going to do now, we are going to design some type of counter circuit in such a way we are going to bring all possible combinations of output. Like we can design, what I can say, if you are going from 0 to 10, like 0, 1, 2, 3, 4, 5, 6, right? So that is called up counter. If you are going from 9, 10, that is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, back, that is called down counter, right? So there are two type of counters are there. Like if you are going from 0, 3, 2, 5, 10, 11, 13, 20, again I am getting back to 7, 5, 3. This is called random counter. So we are also going to design random counter. So these things are all going to lies under, and some other type of things are there. Some ripple counters will be there, mod counters will be there. We will see all those things, right, one by one, right? But prior to that, we have to understand. Now I hope you are getting some basics idea. Counting na normal, சும்மா ப்ராக்டிக்கலாக யோசிச்சு பார்க்கணும். நம்ம கவுண்ட் பண்ணுற எல்லாமே கவுண்டர் தானே, கவுண்டிங் தான். அப்போ நம்ம டிஜிட்டல் சர்க்யூட்டில் எங்கெங்கெல்லாம் வந்து நீங்கள் ப்ராக்டிக்கலாக நம்ம விஷுவலைஸ் பண்ணுற எல்லா விஷயத்தையும் நம்ம டிஜிட்டலில் பார்க்க போகிறோம். ஃபார் தட் we need some circuit, that is simply called counter. That's all, right? Simply understand. So in this case, basically there are two type of counter. One is called synchronous counter and another one is called asynchronous counter. That is the major type of classification. Simply we are calling it as synchronous counter and asynchronous counter. Now, under synchronous counter and asynchronous counter, we are having the major classification. They are called once again up counter will be there, down counter will be there, right? Under up counter, under down counter, we have positive edge trigger up counter, negative edge trigger up counter, positive edge trigger down counter, negative edge trigger down counter. Such a type of circuits also will be there, right? So that is they are lies under asynchronous sequential circuit. Usually they are lying under asynchronous. Similarly, in synchronous sequential circuits also we are going to consider some possible up counter will be there, some down counter will be there, and then we are going to consider some ripple counter will be there. We will see all those things under synchronous counter, right? Now basically what do you mean by synchronous and asynchronous? Just already we have seen the meaning of synchronous and asynchronous in electrical machines itself, right? The thing is there are two type of machine. In AC we have two type of machine. One is called synchronous machine and another one is called asynchronous machine, that is asynchronous machine, that is known as our induction machine, right? That is known as our induction machine, right? So what is the difference between induction machine and asynchronous machine? That is synchronous machine and asynchronous machine. Synchronous in the sense, in case why your synchronous machine is called synchronous machine? I'm just raising the question because in synchronous machine, that is three-phase synchronous machine, we are considering two type of rotation, right? One is we are considering the rotating speed of the rotor, as well as we are also considering the rotating magnetic field, revolving field, right? So there are two persons are revolving inside the machine. One is our rotor, another one is our rotating magnetic field. The rotating magnetic field and rotor are going to rotate at the same speed. They are synchronizing together, right? So they are synchronizing together. That is called a synchronous machine. Now when we are looking for asynchronous machine, that is called induction machine. Your rotor and that is your rotor speed is called simply that is rotor speed only, whereas your that is physical speed of the rotor simply called rotor speed, whereas your one more field, that is called revolving field, rotating magnetic field will rotate around the rotor. That is called what? That is called that speed, that field will rotate at a synchronous speed, right? Rotating magnetic field will rotate at different speed. Your rotor will rotate at a different speed. That is called what? Asynchronous machine, or simply we are calling it as induction machine, right? So coming to the conclusion here. So what do we mean by synchronization and asynchronization? So synchronization in the sense all people will be synchronized together. In the sense, in synchronous machine, what I told you, rotating magnetic field and rotor is being synchronized. Whereas in asynchronous machine, rotating magnetic field and rotor are not synchronized together. They are rotating at a different speed. We have the term is called slip in induction machine. Do you all agree with me? Yes. We have the term is called either it might be single phase or three-phase induction machine, right? Fine. Coming back to the conclusion, it is over. That is the meaning of the synchronization and asynchronization. Now what we are going to do in counters, same thing we are going to realize here also. The thing is synchronization in the sense we are going to consider n number of flip-flops. Like you can assume the box of a train. இப்போ ட்ரெயினில் வந்து ஒரு 10 பாக்ஸஸ் இருக்குன்னு வச்சுக்கோங்க, ரைட்? இப்போ 10 பாக்ஸஸும் வந்து எப்படி இருக்கும் அப்படின்னா, ஃபார் எக்ஸாம்பிள் 10 பாக்ஸஸே வந்து நீங்கள் ஒரே டைமில் மூவ் பண்ணீங்க அப்படின்னா தட் இஸ் கால்டு சின்க்ரோனைசேஷன். நான் ஐம் ஜஸ்ட் ரேசிங் ட்ரெயின் வந்து மூவ் ஆக ஆரம்பிக்குதுன்னு வச்சுக்கோங்க. ட்ரெயின் வந்து மூவ் ஆக ஆரம்பிக்கும் போது நான் டெல் மீ ட்ரெயினோட ஃபர்ஸ்ட் பாக்ஸ் கூட சேர்த்து தான் அகைன் வி ஆர் அட்டாச்சிங் வித் தி ஃபர்ஸ்ட் பாக்ஸ் வி ஆர் அட்டாச்சிங் சம் 20 பாக்ஸ். Separate boxes will be there, separate flip-flops will be there. So all the flip-flops are attached with the first flip-flop, right? So that is the first box. Now first box we are gearing the first box, that is with the help of some engines will be there. We are gearing the first box. Automatically what will happen, your train is started accelerating, right? Here we are going to give clock pulse, right? There we are putting, that is we are gearing the train. Here we are putting the clock pulse, such that what will happen, first that when your first boxes started moving or accelerating, immediately whichever the boxes that are being connected with the first box, they are also going to be accelerated. If your first box is started moving, automatically remaining all boxes are slowly started moving or not. So what is the conclusion here? The conclusion is once your train is attain its rated speed, automatically all the boxes are synchronized together. So whichever the speed that you are observing in the first box, same speed you can observe for all box. That is called synchronization. Can you tell like this, sir, first box is running at 100 rpm, second box is running at 200 rpm. Is it possible? No. How it is possible? Then you cannot attach them. See, இப்போ first box and second box attach ஆயிருக்கு அப்படின்னா they are running at same speed like our synchronous machine, right? Just observe here. Now first box is running at 100 rpm, second box is running at 200 rpm அப்படின்னா they cannot merge together like our what I can say asynchronous machine, induction machine, right? So your train is synchronous machine. All the boxes are what? Synchronized together. Like same thing. Instead of considering train, just to consider the flip-flops. So in case of synchronous flip-flop, that is synchronous counter. Let us coming back. Synchronous counter. All the flip-flops are going to be synchronized with the help of a single clock pulse. Like your train gearing. Train la ஒரு பாக்ஸ்க்கு தனித்தனி engine இருக்கா என்ன? like we are not having like that, right? A single first box is going to be geared accelerated automatically, remaining all boxes, whichever the boxes that are being connected or attached with your train, they are also started moving. So only one clock it is available in the first box. Same way in your synchronous counter, but the thing is, listen, அப்போ மீனிங் என்ன அப்படின்னா, when you are triggering the first synchronous machine, right, that is the first box, at the same time all your boxes are being synchronized, right? So we are going to use a common clock pulse. You can just assume like this, right? So there is a one common clock pulse. That common clock pulse will going to trigger all the, what I can say, boxes together. That is called synchronous counter. Now what do you mean by asynchronous counter? Now asynchronous counter in the sense, first flip-flop will activated, that is because there are many flip-flop will be connected together. Assume like this, first flip-flop will perform its operation, right? Now based on the output of the first flip-flop, that is second flip-flop will be, we have to choose the second flip-flop in order to perform, that is continue its operation. The second flip-flop, right, the working of the second flip-flop will be decided, right? So working of the second flip-flop will be decided based on the output of the first flip-flop. ஃபர்ஸ்ட் ஃபிளிப் ஃப்ளாப்ல வர அவுட்புட் வச்சு தான் செகண்ட் ஃபிளிப் ஃப்ளாப் ஒர்க் ஆகுமா இல்லை ஆகாதா அப்படிங்கிறது இருக்கும், ரைட்? யூ கேனாட் டைரக்ட்லி டெல் தட், இமிடியட்லி யூ கேனாட் டைரக்ட்லி கோ டு தி செகண்ட் ஃபிளிப் ஃப்ளாப். ஸோ இப்போ திங்க் இஸ் வாட், ஃபர்ஸ்ட் ஃபிளிப் ஃப்ளாப் ஒர்க் ஆகிட்டு இருக்கும், செகண்ட் ஃபிளிப் ஃப்ளாப் மே ஆர் மே நாட் ஒர்க். அகைன் third flip-flop is depending on the second flip-flop. Second flip-flop ஓட output வச்சு தான் third flip-flop, either it may work or it may not work. Again fourth flip-flop. So the conclusion is, in case of that is called asynchronization. In synchronization you can simply treat your train a common clock pulse. All boxes synchronized together, they are running at the same speed, they will be synchronized and they will be, what I can say, triggered at the same time. But the thing is, it is not possible in case of asynchronous counter. In asynchronous counter, first we are going to consider one flip-flop and then we are going to consider another flip-flop. First second flip-flop will going to be triggered with the help of first flip-flop. This sequence will be continuous. So here we cannot give assurity that the all flip-flops are always working together in case of asynchronous counter. அப்படி நம்ம சொல்ல முடியாது. First flip-flop உள்ள அவுட்புட் வச்சு தான் நீங்க அடுத்த flip-flop பத்தி பேச முடியும். அதே மாதிரி தான் அதுக்கு அடுத்த flip-flop, right? Yeah, fine. So அப்ப மீனிங் என்ன சொல்ல வர, கன்க்ளூஷன் என்ன கொடுக்குறேன் அப்படின்னா, in case நம்ம ஒரு synchronous counter பத்தி பேசும்போது ஒரே ஒரு கிளாக் that is common to all. ஆனா asynchronous counter பொறுத்த வரைக்கும் என்ன அப்படின்னா, ஃபர்ஸ்ட் flip flopல இருந்து வர வெளியில வர அவுட்புட் தான் செகண்ட் flip flopக்கு இன்புட்டா போகும். That is, it will act as a clock, not input, it will act as a clock, right? So the output of the first flip flop will going to act as a clock for the second flip flop. So that is what I had been told you, based on the output of the first flip flop, second flip flop may or may not be triggered. Again, output of the second flip-flop will going to be the clock pulse of the third flip-flop. So based on the output of the second flip-flop, right, your third clock pulse, that is your third flip-flop, may or may not be triggered. Clear? So this is how we are going to design asynchronous counter. I hope things are very clear to you all, right? So this is the major type of classification that we are going to consider in case of counters, right? So okay, first we are going to happily design what I can say, asynchronous counter, right? We will take asynchronous counter and then we will design synchronous counter. Okay, so keep that in. First we are going to discuss about asynchronous counter. Yeah. See, I will tell you later, there are what is the difference between synchronous counter and asynchronous counter, right? So there are many interesting things are there in between these two guys, right? And you can just do the comparison by yourself at last. I don't want to give these things right now, right? Okay, in asynchronous counter, majorly we have two type of counters, right? Only two type of counters. One is up counter and another one is down counter, right? So up counter and down counter will be decided by the we will see that will be decided by the type of the clock that we are going to use, right? But anyway, in case of asynchronous counter, we are going to use the type of clock, that is the clock that we are going to use is simply called edge triggering, right? So anyway, clock la there are two types irukku. One is called level triggering and another one is called edge triggering, right? I am giving small task to you all after the after end of this session, right? In your free times, just to read. See, don't expect the knowledges from my side itself. You have to enhance by using multiple resources. I am repeating again and again, right? That is the way you have to study. Then only multiple path, that is multiple way of what I can say study things will exist. You can find many resources and that happy happiness will be created, right? So that entire system will going to let you how to study well. right? When you are enhancing your knowledge by using multiple inputs, right? Fine. Anyway, from here you can get more than 90%, right? So rest of things you'll have to enhance. So the conclusion is what? Just try to learn the difference between level triggering and edge triggering. Anyway, after at the end of this session, I'm going to not end of this session. After completing at the end of the sequential circuit, I will demonstrate, right? Okay, fine. Anyway, first you will try to read by yourself. Then it will become very clear to you all. Fine. What we are going to design now, I said there are two major classification. One is called synchronous and another is called asynchronous, like our induction machine, right? So we are going to design asynchronous counter now. So keep that thing. We are going to design asynchronous counter. Yeah, so we are going to design asynchronous counter. First of all, I hope you all remember counter na meaning enanga, just we are going to count like 0 1 2 3 4 5 6 7 8 9. Then up counter up na 0 1 2 3 ascending order, down na descending order. We are going from 9 8 7 6 5 7 like that. Clear? Fine. So that is what we are going to design now, right? So first thing is we are going to design asynchronous counter. I said there are two type of counter. One is called up counter, another one is called down counter. That is the major classification begin of this one. Anyway, I don't want to directly write here. First, let us take some circuits. We will build the outputs, right? Number output la eludhi mudichadukku appuram you will just put the name. Pudichadukku circuit mudichadukku apparama neenga name vainga adu enna circuit அப்படிங்கிறது. Okay, so let me take some things. Okay, fine. Coming back, we are going to use edge triggering here. First of all, adukku mattum na explanation கொடுக்கிறேன், right? What do you mean by edge triggering? Edge triggering அப்படினா here we are going to use a term is called clock pulse, right? First, let me explain a little bit about clock pulse. Don't be panic. At the end of the sequential circuit, I will demonstrate all things, right? Yeah. Now, in edge triggering, there are two type of edge. First of all, what is the meaning of edge? Edge na meaning என்னங்க? For example, நான் வந்து டேம்ல நின்னுட்டு இருக்கேன், ரைட்? ஸோ டேமுக்கு பக்கத்தில் பார்த்தீங்கன்னா டேம் வந்து ஒரு 10,000 feet வந்து ஆழமாக இருக்குது, ரைட்? இப்போ நான் டேமோட எட்ஜில் நின்னுட்டு இருக்கேன். இப்போ நான் கீழே பார்த்தா எனக்கு எப்படி இருக்கும்? That is called edge of me. Do you all agree with me? That is called edge. That is called edge triggering. அப்படின்னா மீனிங் என்ன? See there, this is the height of the dam. நான் இப்போ இங்கே நின்னுட்டு இருக்கேன் and just கீழே எங்கே பார்ப்பீங்க? இங்கே நின்னா கீழே பார்க்க முடியும் இல்லை இங்கே இருந்து பார்க்க முடியுமா? No, exactly. This is called edge. இங்கே இருந்தால் உங்களால் கீழே பார்க்க முடியும். So this is called edge. அப்போ இந்த எட்ஜில் நீங்கள் ட்ரிகர் பண்ணீங்கன்னா that is called edge triggering. ஓவர். சிமிலர்லி சப்போஸ் நீங்கள் கீழே இருக்கீங்க, நான் வந்து டேமு கீழே இருக்கேன், டேமு கீழே நடந்து போயிட்டே இருக்கேன், கரெக்டாக டேமை டச் பண்ணியாச்சு, இப்போ நான் மேலே பார்க்கணும், கரெக்டாக? That is also edge only. You cannot go. Can you cross the dam? No. So that is also edge only, na? இப்போ one more person is sitting here or standing here. He is observing. அவர் எங்கே அப்சர்வ் பண்ணுவார்? கரெக்டாக இந்த இடத்துல வந்ததுக்கப்புறம் this is the edge of this one. You cannot go beyond this. So this is also called edge triggering only. Again, one more person is sitting here and he is observing, which is the edge for him. See, you cannot come back like this. We are going from forward direction. It is, don't reverse the direction, right? Fine. So I am just taking references positive and just we are traveling towards that is positive direction, right? Again, we are reaching. One more person is going here and this is edge. Again, he is observing. Yeah, this is called edge. Sir, அப்போ எல்லா இடத்துலையுமே கிளாக் பண்ணிக்கலாமா? No. Let me tell you that is let me tell you the difference. Side, let me club these two things together. Sorry, these people together. Let us club these people together, right? See there, this is called negative edge triggering. This is called negative edge triggering. I will let you all to understand. Don't be panic. This is called negative edge triggering. Okay? Yeah. Okay, second thing, this is called, right? This is called positive edge triggering. This is called positive edge triggering. Yeah, that's all. So what do I mean here? Your circuit is going to be realized with the help of edge triggering only. அப்படின்னா மீனிங் என்னன்னா, either you can use negative edge triggering or you can use positive edge triggering. So negative edge triggering means whenever you are going from 1 to 0, high level to low level, that is called, right? Whenever there is a down, that is called negative. ஸோ யூஸ்வலாக நம்ம நெகட்டிவ்னா என்னங்க சொல்லுவோம்? நெகட்டிவ்னா மீனிங் என்ன? ஃபர்ஸ்ட் ஆஃப் ஆல் நெகட்டிவ்னா நம்ம நினைக்கிறதுக்கு ஆப்போசிட்டாக நடக்கிறது. லைக் இப்போ நான் ஷேர் மார்க்கெட்டில் ஐ வுட் லைக் டு, நான் வந்து ஒரு எக்ஸ்பெக்டேஷனாக நான் ஒரு 1 lakh இன்வெஸ்ட் பண்ணிட்டேன். ஆட்டோமேட்டிக்லி வாட் வில் ஹேப்பன்? சென்செக்ஸ் வந்து இப்போ நான் இன்வெஸ்ட் பண்ண இடத்துல ஸ்டாக்கில் வந்து ஆட்டோமேட்டிக்காக அங்கே லாஸ் ஆயிடுச்சுன்னா ஆட்டோமேட்டிக்லி ஃபார் மீ ஆல்சோ இட் வில் பி லாஸ். So what will happen? Instead of going, so automatically நான் இன்வெஸ்ட் பண்ண மணி என்ன ஆகும்? That is negative for me. சென்செக்ஸ் டவுனில் போகுதுனாலே what will happen? நான் இன்வெஸ்ட் பண்ண இப்போ நிஃப்ட்டில் பண்ணியிருக்கேன்னு வச்சுக்கோங்க. ஃபார் எக்ஸாம்பிள், ஐ எம் இன்வெஸ்டிங் 1 lakh in நிஃப்ட். It is getting decreased immediately. So what will happen? That is called a negative. right? So negativity means usually ஒரு பாசிட்டிவ்ல இருந்து நெகட்டிவ் போறது அப்படின்னா the expected value இருந்து நமக்கு பின்னாடி போறது, that is very simple, right? So here 1 is our original electrical pulse, but we are trying to get back to the zero potential, so that is 1 to 0, that is usually called a negative, right? Fine. What about positive edge triggering? Positive in the sense we should hike suddenly. இப்போ நான் என்ன பண்ணியிருக்கேன்னா ஷேர் மார்க்கெட்டில் ஐம் ஜஸ்ட் இன்வெஸ்டிங், ஐம் ஜஸ்ட் பையிங் சம் ஷேர், சம் ஒரு 300 இது வந்து வாங்கியிருக்கேன்னு வச்சுக்கோங்க, ரைட்? இன் திஸ் ஷேர், ரைட்? ஜஸ்ட் ஐ வாஸ் இன்வெஸ்டிங் சம் 2 lakhs. Now immediately there was, நான் வாங்கினதுல வந்து ஒரு 10 times வந்து அதிகமாயிடுச்சு என்னோட ஷேர் வந்து, ஐ மீன் ப்ராஃபிட் வந்திருக்கு. ஸோ வாட் வில் ஹேப்பன்? 10 times. ஸோ வாட் வில் ஹேப்பன்? 20, that is a 2 வந்து நீங்கள் 10 times ரைஸ் பண்ணீங்கன்னா automatically become 20 lakhs. I had invested only 2, that is called positive. Is it positive or not? Yes. In electrical pulse it is simply called 0 to 1. In electrical that is called, we are going from switch off பண்ணிட்டு ஆன் பண்றீங்கன்னா that is called positive. In digital that is called 0 to 1. All are practical only. There are no new things we are learning in these subjects. You can just compare these things with the practical circuits, right? Fine. So if there is any hike from 0 to 1, that is simply called positive edge triggering, right? So the thing is, if you are triggering the circuit of a positive edge triggering abdina, your clocks, right? So this is called clock. So let me define, this is called clock now. So clock is a periodic pulse, right? So clock, is it periodic or not? See there, clock is a periodic pulse. This is the one complete cycle of the clock, and this is the correspondent period of the clock, right? Again what will happen? Same pulse is going to be repeated with the same time. Again same pulse will going to be repeated with the same time. Again same pulse will going to be repeated with the same time, and so on. Clear? So that is called what? Periodic pulse, right? So it is keep on running, right? So this is called clock pulse. Here there are 2 type of triggering will be there. Anyway, we are talking about edge triggering, right? I told you just to see the difference between level and the edge triggering. I almost had given the answer, right? Okay, just to try enhance your knowledge, it's enough. Coming back, so edge triggering in the sense you will have to trigger the circuit whenever your value is going from 1 to 0 or 0 to 1. That's all. அப்போ பாசிட்டிவ் எட்ஜ் ட்ரிகரிங் அப்படின்னா கிளாக் பல்ஸ்ல எப்பப்பெல்லாம் வேல்யூ வந்து 0ல இருந்து 1 போதோ, 0ல இருந்து 1, 0ல இருந்து 1, 0ல இருந்து 1, அந்த டைம்ல மட்டும் நீங்க சர்க்யூட் வந்து ட்ரிகர் பண்ணிருக்கீங்கன்னா that is called positive edge triggering circuit. Negative edge triggering அப்படின்னா whenever your value is going from 1 to 0, 1 to 0, 1 to 0, 1 to 0, in that time if you are triggering the circuit, then that is simply called negative edge triggering. Coming back, I hope things are very clear to you all. Let us design the circuit. That is enough, right? Now your asynchronous circuit will be implemented with the help of edge triggering only. We are going to use edge triggering here. Okay, that's why I had been talked about edge triggering. Shall we start our journey? Yes. And the second thing is, actually what we are going to do now, listen guys, listen. In order to design the counter, I only told you we are going to use JK flip-flop and T flip-flop. கொஞ்ச நேரத்துக்கு மட்டும் தான் நான் சொன்னேன் when I was talking about flip-flop. கொஞ்ச நேரத்துக்கு அப்புறம் நான் கவுண்டர்ல நான் கண்டிப்பா இவங்களை பத்தி பேச நான் சொல்லிருந்தேன். That is the point. Now I am discussing. See there are 2 people we are going to use. Either you can use T flip-flop or you can use JK flip-flop, but the priority will be given to you T flip-flop. I am just going with the T flip-flop only, right? You can take anyone. It does not matter here. But the thing is, okay, அப்ப நம்ம T flip-flop எடுத்தாச்சு. Why we are going up with the toggling mode? The thing is, toggling means what? Output is keep on changing. After a particular clock pulse, output is changing, right? So first 0 irukku, again we have to move our state from 0 to 1, again 1 to 0, again 0 to 1, 1 to 0, right? So what is the purpose of changing the state? Then only counting could be possible. See, first I have 0 0 0, next state is what? 0 0 1. How? See, 0 0 0 we are shifting our state from 0 0 0 to 0 0 1. That is we are changing the state, right? We are going from 0 to 1. So that level, that is that toggling, that is called toggling. That is simply called toggling, right? So we are going from 0 to 1. Again there may be a need of going from 1 to 0, again 0 to 1. So that is we are keep on trying to change this state. Changing state is simply called toggling. That could be possible only with the help of JK flip-flop and T flip-flop with the input as 1. When we are giving input as 1 for T flip-flop and JK flip-flop, that is the point where we are going to provide the what I can say toggling. So the conclusion is the entire counter circuits are going to be implemented with the help of JK flip-flop or T flip-flop only with the input of 1. I hope things are clear. Let's start our journey. There are no more things to discuss, right? So we are going to create toggling mode. Toggling mode could be possible only with the help of T flip-flop and JK flip-flop only with the input of 1. First thing, that is over. Now I am going to take what I can say T flip-flop immediately. First I am not going to discuss anything now. First we are going to perform the operation and then we will gather the information. We will analyze the circuit, right? That's much better. Let me rub all these things. Okay, this thing settle does not require. Fine. let's start. Okay, now let me simply consider 3 T flip-flop here. Class is going good, huh? Yeah. Okay, fine. So we are considering 3 flip-flop, right? Now what I am going to do? Let us assume that I am giving negative edge triggering. Slowly understand, right? Okay, so this term is simply called Qn. Of course, here you will have one more output, that is Qn bar. This is Qn. There is one more output, that is Qn bar. This is Qn. There is one more output, that is Qn bar. Now, next we are going to provide the input. I told you that I am going to use T flip-flop. Input is what? 1. Yeah, we are going to use T flip-flop here. Now, let us call this one as Qn0, Qn1, Qn2. Okay, guys, listen. This is your MSB, and this is going to be your LSB. We are going to start our operation from here only. Anyway, while writing the bits, what we have to do? We will have to count from here only. This is the point where we are going to collect the outputs. We will see. First, I will complete these things, right? Now, let us start the operation from here. See, this is called, if your clock is being represented with a bubble, right, like this, then that is called, in the circuit, if you find like this, then that is called what? Negative edge triggering. Or simply write first a negative clock pulse, because edges, we are also trying to give level triggering. That could be later, we will see, right? So here that is simply called a negative clock. We can simply write this one as negative clock. So if it is given like this, then that is called a positive clock. Fine. So this is called what? Negative clock. Fine. Shall we start our journey? Okay, fine. So initially, let us assume outputs of all flip-flops are 0, right? So let us draw the waveform for, guys, simply call, this is why I am putting Qn. I am just in the flip-flop mindset layer. Just put like, okay, fine, wait a minute, see there. Fine, that's fine. Shall we start? Okay, immediately. I told you we are in what? Asynchronous counter. Asynchronous counter basic things. நம்ம என்ன கத்துக்கிட்டோம்? Asynchronous counter பொறுத்த வரைக்கும் என்ன அப்படினா second counter. இந்த counter வந்து இது activate ஆகாததும். I mean this flip flop, right? So the active state of this flip flop is depending on the output of the previous flip flop. Similarly, this flip flop, right? Activation of this flip flop is depending on the output of the previous state of the flip flop. That is previous flip flop, right? This output only will going to decide this one, right? Okay. Second conclusion is, listen, when this flip flop will be triggered. Actually, what do you mean by negative edge triggering and positive edge triggering? That's just now I had given the conclusion. Since it is called a negative edge triggering, it means whenever your clock is going from 1 to 0, that is the point where your flip flop will be triggered. Do you all agree with me? That is called a negative edge triggering, right? So first, let me draw some clock here. So let me draw some clock, right? So listen. Let us take the clock pulse. Right, slowly understand how many clocks should be required, everything you only decide. I told you we are going to do analysis only, right? I cannot directly tell the story of these circuits, right? We have to understand the beauty of the circuit. That's what I want from your side. Fine. So since we are going to design, that is this is clock. In the clock on the end enter in the train on the enter, right? So here, since we are designing what, that is negative edge triggering, negative edge triggering, negative edge triggering, negative edge triggering. Negative means we are going from what? 1 to 0, 1 to 0, 1 to 0, 1 to 0, and so on. Am I clear? Yeah, fine. Let us see. Just let me draw a pattern exactly when we are triggering this circuit. Slowly observe. It's really quite interesting actually. I said in digital there is no point of memorizations. It's like a game because we are designing a digital circuit. Fine. Now first step, I would like to draw the output pattern for the first flip flop, this one, right? So let us consider. Let me consider Q2 flip flop. Output of the first flip flop. right? Forget about the rest of flip-flop. First only consider the first flip-flop. Now since we are in toggling mode, what do we mean by toggling mode? Toggling means state of the output is keep on changing from 0 to 1, again 1 to 0, again 0 to 1, again 1 to 0, again 1 to 0, 0 to 1, again 1 to 0. That is called a toggling mode. Already this observation we have done in the output of JK flip-flop under what I can say T flip-flop also, right? So the conclusion is whenever your input of the T flip-flop is going to be 1, right, your output of the flip-flop is keep on triggering, right? So keep on toggling. What do I mean? What do you mean by toggling? Toggling in the sense, see there, for an example, நீங்க first clock கொடுக்கும்போது இப்போ இந்த flip-flop மட்டும் எடுத்துக்கோங்க, right? இந்த flip-flopல first clock, right? So whenever clock of this flip-flop is going from 1 to 0 போகுது அப்படினாலே immediately state of the circuit, output state of the circuit will change. Again அடுத்த clock வந்து திரும்ப எங்க 1 to 0 போகுது, திரும்ப என்ன ஆகும் அப்படினா state change ஆகுதுனா மீனிங் என்ன? Very simple. Whenever your clock is going from 1 to 0, for an example, initially output is 0. Initially output is 0. When we are giving first clock, when your clock is going from 1 to 0, that is called first clock, it's changing its state. Again when your clock is second time, when it goes from 1 to 0, because negative edge triggering in the sense you will have to consider only negative spikes. Now again when we are going from 1 to 0, its state will change. Again its state will change. Again its state will change. That is called toggling mode. Let us see. இப்போ என்ன ஆகுதுன்னு பார்க்கலாமா? Initially let us assume all the initial outputs are 0. இனிஷியலா அங்க அவுட்புட்ஸ் கிடையாது. ஃபர்ஸ்ட் flip-flop ஓட அவுட்புட் 0 னு வெச்சுக்கோங்க. இப்போ நீங்க என்ன பண்றீங்கன்னா, see there, this is the first clock. இப்போ நீங்க ஃபர்ஸ்ட் டைம் இத கிளாக் பண்ண உடனே anyway it is toggling because input is fixed, so it is keep on toggling. கிளாக் வரும்போது toggle ஆகும், state change ஆகும். See there, when we are giving first clock, automatically it's changing its state from 0 to 1. And its level will be maintained as constant until the arrival of the next clock pulse. See, immediately we are giving the next clock pulse after a certain time period, right? That is called clock time. And then this is the time where we are triggering the circuit once again, same flip-flop. Now what will happen? Output of the flip-flop immediately will change from 1 to 0. That is called toggling mode. It is keep on toggling like a spring, right? So next what will happen? Immediately after, again we are giving clock here. If you are giving next clock pulse, once again it's changing. That is called toggling. It's going from 0 to 1. Again in the next clock, again it is going from 1 to 0. Again it is going from 0 to 1. Again it is going from 1 to 0. Again it is going from 0 to 1. Again it is going from 1 to 0. It's and so on. Clear? So let me register the variable. This is 0, this is 1, 0, 1, 0, 1, 0 and so on. Clear? Now what I had been told you, output of the first flip-flop is going to be the input of the next flip-flop. That's why I told you don't consider the rest of flip-flop at all time. That is, you cannot consider all flip-flops at a time in case of asynchronous counter. In synchronous that could be possible because synchronous like a train, all trains will going, that is all the boxes of the train will going to be synchronized at a single time. But here it is not possible. Your second flip-flop will be, that is output, that is output of the second flip-flop will be decided by the output of the previous flip-flop, because it is going to act as a clock for this one. Let us see, this is the output of the first flip-flop. Yes, let us see, since we are using what, negative edge triggering, it means now you can treat this one as a clock. You can treat this one as a clock because this is going to act as a clock for this flip-flop. Let us see. Now here, whenever this value is going from 1 to 0, 1 to 0, 1 to 0, 1 to 0, that is the point where this flip-flop will be enabled, triggered. I told you initially all flip-flop outputs were assumed to be 0 only. Now tell me at which point this flip-flop will be enabled. This flip-flop will be enabled, right, when this clock pulse, this is the clock, this is the clock, இதுதான் இந்த clockல எந்த இடத்துல value 1 ல இருந்து 0 க்கு வருங்க, this is the first time where your value is going from 1 to 0. So until the arrival of the first clock pulse, there is no changes in the output state of the flip-flop. So immediately we are giving this one as the clock now. So this is going to be triggered your flip-flop, right? This triggering will going to automatically enable the flip-flop, right? So happily, see, since we are in toggling mode, whenever your flip-flop will be triggered, immediately it is changing its state. So initially it was 0, now it is changing its state to 1. State to 1. So until the arrival of the next negative clock pulse, there is no changes in this state. See there, now this is immediately after reaching this point, it will act as a clock now, so it will trigger the flip-flop once again. So immediately your circuit will change. So it will goes from 1 to 0, 1 to 0, 1 to 0. It will maintain. Again, it will become remains constant until the arrival of the next clock pulse. Yes, this is the point where we are giving next clock pulse. So immediately it will change its circuit from, that is a change its state from 0 to 1. So until the arrival of the next clock pulse, there is no changes in this state. It will be remains maintained as constant. Again, it will goes from 1 to 0. Again, it will goes from 1 to 0. What is the conclusion? That's all. This is the output. Now, output of the second flip-flop will going to act as a clock for the third flip-flop. But which clock? Either it is positive triggering or negative triggering. We are considering negative edge triggering. Where is the negative spike for the second flip-flop output? See there. Output of the second flip-flop will going to act as a input of the third flip-flop. So this is the output of the second flip-flop. Where it goes from 1 to 0, this is the point. Again, where it goes from 1 to 0, this is the point. So until the arrival of the gate pulse, there is no changes in the output state. So initially all flip-flop outputs were assumed to be 0. So once again it started from 0, 0, running until the arrival of the clock pulse. There is no changes in the state. Again, when we are facing the first clock, again toggling will be there. It's changing its state from 0 to 1. It's setting. See that it is continuous. It is continuous. Until the arrival of the second clock pulse. Immediately after reaching this point, it will go here. Why? Because we are providing the next clock pulse. Clear? It's over. This is Q2, this is Q1 output, this is Q0 output. Let me register the variables. 0, 0, 0, 1, 1, 1, 1. This is going to be 0. Shall we start our count? We should start from here. This is the final, right? We have to start the count, right? You will have to write the output like this. Q0, Q1, Q2. Because here only we are going to collect the data, right? So let us register the value. Write the variables from MSB to LSB. Clear? Like this, in this format. Very simple. From here to here, we will have to just arrange the order. Arrange let us start the count. See there, I will have to start from Q0. Observe, Q0 is 0, Q1 is 0, Q2 also 0, such that we are getting 0, 0, 0. Clear? Now, here I have not given any trigger. That is, your circuit is not being triggered yet, right? So with the 0 clock, I have not. Where shall we write? Actually, shall I write there? Because here we don't have space. Fine. Let us start our journey with this one. Q0, Q1, Q2, this is going to be our clock pulse, right? Now, till now, I did not given any clock pulse. See that the first clock is centering at this point only. Guys, listen, this is your original clock. Don't forget that one. This is your original clock. This is the heart of the whole circuit. Actually, the thing is, output of the first flip-flop will going to act as a, that is clock of the second flip-flop. It does not mean that this is the original clock. This is your original clock. You will have to, after completing the whole operation, you will have to treat this one as the reference clock. You cannot consider these things as your clocks. This is your reference clock. Clear? He is your hero. Okay, let us see. Now, when your clock is 0, I had not applied any clock. See that this is the first point we are going to apply the clock. Until the arrival of the first clock, there was no changes in the set. See there, Q2 is 0, Q0 is 0, Q2, Q1, Q0 all are 0, right? Such that without applying clock pulse, initially all were assumed to be 0. When I am applying the first clock, where we are applying, this is the first clock points. Immediately after the application of the first clock, observe the state 0, 0, 1. So we are getting 0, 0, 1. See there, Q0, Q1, Q2, right? The variables are going to be 0, 0, 1. Let us consider. Next we are going to consider. See there, this is the second clock pulse. See there, first clock pulse, second clock pulse, third clock pulse, fourth clock pulse, fifth clock pulse, sixth clock pulse, seventh clock pulse, eighth clock pulse. Fine. Let us see exactly in the second clock pulse. Once again, state is changing from 0, 0, 1 to 0, 1, 0, right? So it is changing. When we are applying the second clock pulse, it is going from, that is 0, 0, 1 to 0, 1, 0. Let us see when we are applying the third clock pulse, again state is become 0, 1, 1, right? Your state is, next state will become 0, 1, 1. Now when we are applying fourth clock pulse, right? Now where is your fourth clock pulse? This is the fourth clock pulse. Right? When you are applying fourth clock pulse, again outputs become 1, 0, 0. So it is become 1 0 0. When we are applying fifth clock pulse, let us see. When we are applying fifth clock pulse, this is output state become 1 0 1. Again 1 0 1. Now when we are applying sixth clock pulse, right? So this is, where is your sixth clock pulse? This is the sixth clock pulse. Output will become 1 1 0 1 1 0. When we are applying seventh clock pulse, again it is become 1 1 1. When we are applying seventh clock pulse, it is become 1 1 1. Now when we are applying eighth clock pulse, right? So while applying the eighth clock pulse, this is eighth clock pulse, we are getting back to the original state, that is the initial state. So totally, in order to complete one's complete cycle, in order to complete, right? So see there, I have just started from 0. This is initial state. Without applying clock, I was standing here. In the first clock, I have started my journey here. I was just running up to 7. Exactly at the 8th clock pulse, we are getting back to the original state at the 8th clock pulse. Clear? So totally, 8 clocks are required in order to complete one complete set. Guys, listen. In the 7th clock pulse, you are standing at 1 1 1. Now in order to, again you will have to திரும்ப நீங்க என்ன பண்ணனும் 0 ல இருந்து ஸ்டார்ட் பண்ணனும். அப்ப நீங்க என்ன பண்ணனும், see there initial state நான் என்ன சொல்லிருந்தேன் 0 0 0 தான செட் பண்ணிருந்தேன். அப்ப நீங்க திரும்ப என்ன பண்ணனும், initial state 0 0 0 செட் பண்ணனும் அப்படினா you will have to apply what, லாஸ்டா நீங்க 8th clock pulse அப்ளை பண்ணனும். 8th clock கொடுத்தீங்கன்னா தான் என்ன ஆகும், circuit is getting back to 0 0 0. that is the 8th clock pulse. So அப்ப மொத்தமா எத்தனை இருக்கு பாருங்க, எத்தனை ஸ்டேட்ஸ் இருக்கு பாருங்க, 1 2 3 4 5 6 7 8. this is called a number of states. This is called a number of counts. How many counts I have done here? 0 1 2 3 4 5 6 7, right? Totally how many counts are there? 0 is also a count, right? So count number, count 1, count 2, count 3, count 4, count 5, count 6, count 7, count 8. That is called mod 8 counter, right? So name of this circuit, right? So first it is called mod 8 counter. Modulus magnitude, right? That is modulus 8 counter. It is called mod 8 counter. Let us see. And another thing is, if you observe the order, we are going from 0 to, and then next state decimal equivalent. See there 0 0 0 0 0 1 0 1 0. What is this? Decimal equivalent is, this is its decimal equivalent is 0, its decimal equivalent is 1, its decimal equivalent is 2, it's 3 4 5 6 7. What is this? Up counter, ascending order, right? So that is called, it is also called up counter. It is also called up counter. Do you all agree with me? Yes. And the next thing is, let us see where we are receiving our output. The thing is, so we are collecting the data from these 3 guises. We are collecting the data from these 3 guises, right? So if you observe the frequency of each and every persons, let us see. Let me calculate the frequency of all these guys, right? Okay, let us do all these things one by one. First of all, what we have, that is we named the circuit, and second thing is, next we have to observe how many clocks that are should be, how many clocks are required here. See there, the total number of clock is 8. So can I say number of clocks and number of states are equal, right? So the next thing is, you can write, right? Number of states should be equal to number of clocks. Clear? So number of states should be equal to number of clocks, right? So anyway, total number of states are what? So in our case, number of states are 8, right? So let me define next thing. So let me write a relation here, 2 power n greater than or equal to caps n. What is this? Here, this n denotes the number of flip-flops, whereas this n denotes the number of states or counts. How many states here? How many states? 8 states. 1 2 3 4 5 6 7 8. Totally we got 8 states, such that if here n will become 8 states, if n is equal to n, sorry, if this capital N equal to 8, then for what value of n, for what value of small n we are getting this 8. See that relation is 2 power n is greater than or equal to n. That is the general relation between number of states and the number of flip-flops. N denotes number of flip-flops, small n denotes the number of flip-flops, capital N denotes the number of states. Now here, this small n is what? How many flip-flops you are taking here? 3 flip-flops, right? So with the help of 3 flip-flops, you can count 8 states. So which is greater than or equal to, number of states we got 8 only, na? Yes, condition is satisfied. Suppose if you want to consider if you want to count 12 states, if you want to count 12 states, then what is the minimum number of flip-flops that it should be required? The question is 2 power n is greater than or equal to the value of n, where small n denotes the number of flip-flop, capital N denotes the number of states, right? So the conclusion is, from here, if you want to calculate the value of n, just take the log with the base 2, such that log with the base 2, right? So here what we are going to get, log with the base 2, here we are going to get 2 power n equal to, right? So that is greater than or equal to, here also we are taking log n only, right? So where shall I write? Is that portion is visible to you all? Yeah. Guys, listen, let me write it here actually. See, நீங்கள் ப்ராப்பராக எழுதுங்க, ரைட்? ஸோ ஃபஸ்ட்டு ஸ்டெப் இதை எழுதிக்கோங்க. நீங்கள் இதை முடிச்சிட்டிங்களா? முடிச்சதுக்கப்புறம் கீழே 1 by 1 எழுதுங்க. ஃபஸ்ட்டு why we are calling it as mod 8 counter, take write down the reason. Why we are calling it as up counter, write down the reason. Next, which is called number of states. Number of states in some means number of possible combinations that we are getting in the output. And how we are calculating the number of clocks, next step. And then write down the next step, right? So next the thing is the relation between number of flip-flop and the number of states. Next எழுதுங்க, right? So the relation between, step by step neat எழுதுங்க, right? So the number of states, because here I don't have space, that's why I am writing somewhere, right? So this is not the correct way to write in your notes. 2 power n greater than or equal to n, fine. So let us continue. See that just what I have been told you, in order to calculate the number of flip-flop, just raise the log base to 2 power n greater than or equal to log base to n. Now from here, this is going to be what, which is equal to n, because we all know log base a, here it is a power b, which is equal to what, b only. So this is become n, right? So it is greater than or equal to log base to n. Now from this, if you substitute, right, இப்போ நீங்க n க்கு வந்து value substitute பண்ணீங்க அப்படினா, see there, where is n? n is 12. Anyway, you can directly guess it. Listen, நீங்க n வந்து இங்க 12 னு போட்டீங்கன்னா, capital N 12 னு கன்சிடர் பண்ணீங்கன்னா, we know n க்கு வந்து நம்ம 3 னு போட்டா we are getting 8 only. இதை நீங்க n க்கு 4 போட்டீங்கன்னா we are getting 16. So 16 ல நம்ம என்ன பண்ணிக்கலாம், 12 states we can bring, rest of 4 states are going to be invalid, such that we can, I mean 4 flip-flops, directly we can tell the answer. We no need to do this blob story, because in your examination at sometimes you will be tested with some theoretical questions. What is the relation between number of states and number of flip-flop, right, in counters? If you don't remember that's why I am writing this relation. You are not supposed to do any calculation with this. Coming back to here, you can simply calculate here. So totally I made of 12 states. 12 states வரணும் அப்படினா 2 power 3 ஆல கொடுக்க முடியாது. So next possibility 2 power 4 only. So 16 states, so you can consider 12 states, rest of 4 states are considered as invalid states. So like that you can simply guess the number of possible flip-flops. Clear? That's all. I hope things are very clear to you all, right? Anyway, next conclusion. So next we have to calculate the frequency, right? So what I have done, I am repeating once again. First you have to consider the number of states and then count the number of clocks, right? That is number of states and the relation between number of clocks. And initially இதை எழுதுறீங்க, அதுக்கு முன்னாடி why it is called up counter, what is the reason why it is called mod 8 counter, right? How many counts are there? Totally 8 counts, that's why that names at all. And then find out the relation between number of flip-flops and the number of states, and then let us write the frequency, right? So frequency in the sense, guys listen, in the input side this is our clock, right? So let us define that is the time period of one clock, let me call it as t. Time period of one clock is, let me simply call it as t. Now if you observe, this is the original clock, this is the original clock time period. இப்போ நீங்க observe பண்ணி பாத்தீங்க அப்படினா, first flip-flop for output is going to be act as a clock for the second flip-flop, correct? So if I will consider this one as the clock, இப்போ இத நீங்க observe பண்ணி பாத்தீங்கன்னா, what is the frequency of the output of the first flip-flop? Frequency of the output of the first flip-flop, right? Either frequency பாருங்க, what do you mean by frequency actually? See, first of all, frequency in the sense, right? Frequency or time period. Okay, let me talk in terms of time period itself. Time period அப்படினா time taken by the output in order to complete one cycle. What do you mean by one cycle? You will have to consider positive as well as negative. That is the periodicity, right? So period of one complete cycle is this much. Now if you observe, if you just compare it with our standard clock pulse, see there in between இங்க எத்தனை clock இருக்கு பாருங்க, this is one complete clock, this is one complete clock. So what is the meaning? Input sideல உங்களோட clock period வந்து 2 cycles complete பண்ணும்போது தான் இது 1 cycle complete பண்ணுது. So can I tell like this? So what is the conclusion here? The conclusion is, suppose if your input clock pulse, right, input clock pulse oda time period, for an example if I am just calling this one as the frequency, time period வந்து t, இதோட corresponding input frequency வந்து நீங்க fn அப்படின்னு சொல்றீங்க அப்படினா, right? அப்ப first flip-flop இதோட output frequency எவ்வளவு வரும் அப்படினா, right, frequency of this output is going to be, first flip-flop output is input frequency divided by 2, because time period will be doubled. Time period will be doubled. See there, I am taking twice of the clock period in order to complete the one cycle. I am taking twice of clock in order to complete one cycle. If you observe the next one, இதை கவனிச்சு பாருங்க. ஜஸ்ட் கன்சிடர் first clock, second clock, third clock, fourth clock. Totally I took 4 times of t in order to complete one cycle. அப்போ frequency என்ன வரும்? For this person your output frequency, right, this is going to be f divided by 4. Frequency will be 4 times reduced because time is 4 times increased. I am taking 4 times of t in order to complete one cycle. Similarly, if you observe the last person, we are going from, actually we have to consider, see there, either you can include this 0 or you can include this 0. If you observe 1t, 2t, actually we are not applying clock here, so you can consider the last one at least. This 1t, this 1t, this 1t, here 1t. Totally 1 off. 4t, here 1t, 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 4t. How many t we are taking? 8 times of t. Input actually நம்ம set பண்ண time periodல 8 times of t we are taking in order to complete the one complete cycle of the third flip-flop, such that its frequency is going to be, output frequency is going to be f divided by 8. f divided by 8. I hope things are very clear to you all now, right? So that is how we are finding the frequency of the outputs. Okay, just to make a note of it, because everywhere you will be tested, right? So everywhere you will be tested with this. Okay, fine. And next thing is, here you will also be tested for duty cycle, right? Now what do you mean by duty cycle? Duty cycle in the sense, in power electronics already we had been observed, right? Duty cycle அப்படிங்கிற term எங்க பார்த்தோம்? It was in choppers, right? We are know, yes. So duty cycle in the sense, effective time period, right? So like I said, the example is watchman, right? Everywhere duty அப்படிங்கிறது வாட்ச்மேனுக்கு மட்டும் கிடையாது, right? நமக்கும் டியூட்டி இருக்கு இல்லையா? Morning we are taking the classes, evening we are taking the classes out of 24. So what is the duty cycle of me with respect to the class time that I am taking, right? So the thing is, for me duty cycle is, let me call it as class எடுக்கிற time, just we are calling it as on time or active time. Let us take classic number duty cycle calculate பண்றோம், right? So at on time divided by total time period. So what is the duration per day? The total duration per day is 24 hours. How many hours we are taking the classes? Only for 5 hours. That is simply called duty cycle. So on time period is simply called a duty cycle. Active time period is simply called a duty cycle. So in that way, if you are writing the duty cycle for the output, இப்போ நீங்கள் அவுட்புட்டுக்கு வந்து டியூட்டி சைக்கிள் எழுதுறீங்க அப்படின்னா, how will you write? You can write like this. See there, outputல ஆக்சுவலாக எத்தனை ஸ்டேட் இருக்கு அப்படின்னா 8t we are considering. கரெக்டா? 8tல எவ்வளோ டைம் வந்து நம்ம ஆக்டிவ்ல இருக்கோம்? See there, here active statesனா 1. Totally for 4t your circuit will be in on state. Out of 8t we are considering 8 times of the clock time period in order to complete one cycle in output. That is the, I am just giving what I can say example for example. I am just giving example. I am calculating duty cycle for last flip-flop. You can also check it for this one like this. So duty cycle in the sense, on time divided by total time. On time denotes high, pin is high, output is 1. So totally we are considering 4t. If I'll cancel it, it is become what? 1 by 2, or in percentage 1 by 2 means 0.5. In percentage that is called 50%. So duty cycle is 50%. Clear? Similarly you can also calculate for this one. This is what? Out of 4t we are getting 2t as the output, enable portion. 2t by 4t, again we are getting 50%. You can also consider the first one. Out of 2t, 1t is the output, so t by 2t, again we are getting 50%, right? So that is how we are calculating duty cycle for your outputs, right? Clear? I hope things are very clear to you all. So this is all about up counter, right? Anyway, after we have just named like this, now I would like to do small changes here, right? So what I am going to do, the thing is, instead of giving negative clock pulse, I am taking same circuit, but I would like to give positive clock pulse. இதனால ஏதாச்சும் சேஞ்சஸ் வருமா சர்க்யூட்ல? தெரியலையே, செக் பண்ணிடலாமா? எஸ், that is our next target. I'm just taking positive clock pulse. Okay, fine. I hope things are clear to you all. Let's rub all these things, because I don't know what will happen, because we took new circuits, right? We took a new circuit. See, we have to analyze, right? Just I'm doing analysis only, but it is quite interesting. Did I teach you any new things here? No. Just we are learning something in a new way, right? Things are known, but we are learning it in new way, right? Fine. Okay, let's start. See what I took here, I'm just taking positive clock pulse. I don't know anything, just I'm having circuit with me. I have to decide, right, what type of circuit அப்படிங்கிறத ஃபைனலாக தான் நம்ம whichever the analysis that we have done for the last case, same thing you are requested to do the for this one, right? First step, draw the clock pattern, right? So let me start with the clock. Okay, what type of clock it is? Positive edge triggering. Abdina meaning enna? Whenever we are going from 0 to 1, 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 simply we are calling it as positive edge triggering, right? Fine. So let us extend the pattern. Okay, what we need to do, we need to draw the output waveform. Start பண்ணலாமா? Q2, Q1, Q0, right? Yeah. That is going to be Q2. Once again, same operation. Initially you are assumed to, that is you are requested to assume the value is 0. Now when we are giving the first clock கொடுத்தோன்னா என்ன ஆகும்? It is called toggling state na. So 0, it's raising its value from 0 to 1, it's going to 1. Again while giving second clock pulse, it is going from 1 to 0, again 0 to 1, again 1 to 0, again 0 to 1, again 1 to 0, again 0 to 1, again 1 to 0. So 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0. It's keep on raising its value. Second case, இப்போ அடுத்து என்ன வரணும்? Output of the first flip-flop is going to act as a clock for the second flip-flop. But since we are using positive edge triggering, so whenever your clock is high, that's giving its value from 0 to 1, 0 to 1, 0 to 1, 0 to 1. That is the point, there will be changes in the output. Let us see. Second flip-flop, initially all values were assumed to be 0. So let us assume initially it is 0 only. But while giving first clock, see there, it will going to act as a clock. Going to act as a clock for the second one. So with the help of this one, immediately we can control the second flip-flop. Let's see. When we are initially it is 0 now. So the first state will become immediately 1. Right, so until the arrival of the next clock pulse, there is no changes in the output, it is remains constant. Again in the second clock pulse, it's changing its state. Again in the third clock pulse, it's changing its state. Again in the fourth clock pulse, it's changing its state. Clear? So see there, this is going to be the clock, this is going to be the clock now. So the output of the second flip-flop will going to act as a clock for the third flip-flop, such that, see there, initially I am assuming the output of the last flip-flop is 0 only, but this is going to act as a clock na, such that it is become 1 and it is continuous until the arrival of the next clock pulse. Immediately after, it is again toggling and it is reaching 0 until the arrival of next clock pulse. It's just continuous, right? Fine. I hope things are clear to you all. So next what we are going to do, okay, let me write down the states. So 1 1 1 1 1 0, this is 1 0 1 1, what is this? This is 1 0, this is 0 0 1 0 0 0 1 0 0 0 1, again 0 0 0. Fine. Shall we start our journey? Yes. Let us see. இப்போ எழுதலாமா? Just a clock Q2, sorry, Q0 then order, first Q0, Q1, Q2. Initially, prior to the clock pulse, right, all initial values are assumed to be 0 only. When we are giving first clock pulse, there is a hike. See there, 1 1 1. You will have to start your count from Q0, 1 1 1. So I am getting my outputs are as 1 1 1. Now when we are giving second clock pulse, while giving second clock pulse, it is going to be 1 1 0, 1 1 0. While giving third clock pulse, it is going to be 1 0 1, right? While going third clock pulse, it is going to be 1 0 1. For the fourth clock pulse, it is going to be 1 0 0. For the fifth clock pulse, it is going to be 0 0 1. For the sixth clock pulse, it is going to be 0, sorry, wait a minute. Fourth clock pulse enga irukudha? See there, what is this? 0 1 1 na? I made mistake, right? So this is 0, correct போகுதா? Yes. Next, while giving a sixth clock pulse, this is 0 0 sixth clock pulse இங்க இருக்கா 0 1 0, this is going to be 0 1 0. Yes, while giving seventh clock pulse we are coming back to 0 0 1. While giving eighth clock pulse we are back to initial state. That's what I had been told you, right? So this is eighth clock pulse, we are getting back to the first state, initial state, right? So totally am I correct? 1 2 3 4 5 6 7 8. Of course I am correct, right? Now just shall we name the counter? Yeah, how many counts states are there? 1 2 3 4. See there, eighth clock pulse, in the sense this is, you can treat this one as 8. We no need to unnecessarily need here one more state. How many states are there? Totally 8 states are there. So what type of counter it is? This is also called mod 8 counter only, right? But this is called, last case your counter is called mod up counter, right? So last case நம்ம பார்த்தது mod up counter. This is called mod down 8 counter, right? So this is mod down 8 counter. Mod 8 down counter also we can call like this. Anyway, what type of counter it is? Is it down counter or up counter? See there, we are starting from 7, right? And then 6 5 4 3 2 1 0. What is this? What type of counter it is? It is simply called a down counter because it's counting its value in the descending order, right? So it is called down counter. It is called down counter, right? Now rest of things are remain same. There is no changes in the, see the number of states, totally we are getting 8 states. Number of states equal to number of clock pulse, and the number of states equal to what? See, number of flip-flop should be equal to, same relation you can use because I have not changed anything. We are, since we are going up with the same 3 flip-flop only. Clear? So that is how we are designing counter circuit. Now I am just giving one more task to you all. இப்போ நீங்க என்ன பண்றீங்க அப்படினா, take this same circuit, but இப்போ என்ன பண்றீங்கன்னா இத மாத்திக்கோங்க. எங்க இருந்து வரீங்க? இது உங்களோட ஒர்க். எனிவே நான் நாளைக்கு கண்டிப்பாக பண்ணுறேன், உங்ககிட்ட நான் கொடுக்குறேன், நீங்கள் அதை வரீங்கன்னு நான் சொல்கிறேன், அவ்வளோதான், ரைட்? யூ ஆர் ரெக்வஸ்டட் டு நெக்ஸ்ட் ஃபிளிப்-ஃப்ளாப் வில் பி ட்ரிகர்ட் வித் தி ஹெல்ப் ஆஃப் கியூ அண்ட் பார். எப்படி சார் ஃபைன் பண்ணுவீங்க? வெரி சிம்பிள். ஐம் ஜஸ்ட் கிவிங் பேசிக் ஐடியா. கவனிங்க, நீங்கள் இங்கே ஃபஸ்ட் டைம் கிளாக் கொடுத்த உடனே என்ன ஆகும்னா, இனிஷியலாக இது 0 இருக்கா, இனிஷியலாக 0. ஃபஸ்ட்டு கிளாக் கொடுத்த உடனே இது 1ன்னு செட் ஆகும். இங்கே 1 வரும்போது இங்கே என்ன வரும்? 0. தட்ஸ் ஆல். நீங்கள் 1 எடுத்துக்க முடியாது இல்லையா, பிகாஸ் இங்கே 1 வருதுன்னா போத் ஆர் காம்ப்ளிமெண்ட் ஆஃப் ஈச் அதர். போத் ஆர் காம்ப்ளிமெண்ட் ஆஃப் ஈச் அதர். both are complement of each other. So நீங்க என்ன பண்ணிக்கலாம்னா, ஃபர்ஸ்ட் இந்த அவுட்புட்டை நீங்க ப்ரெடிக்ட் பண்ணிக்கலாம். இதுல இருந்து இங்க என்ன வருதுன்றதை நீங்க கெஸ் பண்ணிக்கலாம். இதுக்கு வரதுக்கு அப்படியே காம்ப்ளிமெண்ட் எடுத்து just to draw the clock pattern. Just to try, enhance your knowledge, right? Don't expect the answer flow always from my side. It's your responsibility. I hope things are very clear to you all, right? So with this, let's wind up the today class, right? There are two possibilities. Listen guys, இங்க positive clock இருக்கா? Positive clock with this input. Second positive. Next வந்து negative clock with the same input. இதே இடத்துல input எடுத்துட்டு இது அப்படியே நெகட்டிவா மாத்தினா என்ன ஆக போகுது? Same thing you can observe. Once again you are going to get down counter and up counter only. You please check. You please do it by yourself. என்ன பாசிபிலிட்டி வருது அப்படிங்கறத நீங்க செக் பண்ணி பாருங்க, ரைட்? அது ஆட்டோமேட்டிக்கா உங்களுக்கு புரிஞ்சிடும். ஒன்ஸ் நீங்க அண்டர்ஸ்டாண்ட் பண்ணிட்டீங்கன்னா ரிமைனிங் அதுக்கு அடுத்து நம்ம டிசைன் பண்ண போறதெல்லாம் ரொம்ப ஈஸியா இருக்கும். It's over. That's all, right? So today class is over with this. If you have any doubts, you can ask in the group. With this, let's wind up the class. Thank you all. Wind up.